The objective for today's lab was to answer the following questions. What is static equilibrium and what is torque?
Alright, so the theory for our lab comes from these two equations. The first one is that force equals mass times acceleration, where force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. And then the second equation is torque is equal to force times the lever arm, where torque is measured in newton meters, force again in newtons, and the lever arm is measured in meters. Now, what exactly does the lever arm mean? It's talking about the perpendicular distance from this axis of rotation to a line of action. And we see here that it makes a right angle. And now, why is there a distinction between force and torque? And as you can see here from this circle, when an object is moving with circular motion, they will have a certain angular displacement, which is the same no matter how far away from the center you measure it from. Whereas if you just measured it as a straight line, you would get a different distance. And so that's why there are different rules for circular motion versus linear motion and why we need these separate equations. The other part of our theory is that for any system in equilibrium, we will always have a net force and a net torque about any axis equal to 0. And so we can see that with 3 examples. In this first example, the system, the forces, the up and down forces are equal, so they cancel each other out. However, the net torque about this axis of rotation is not equal to 0, and so this system will continue to spin and will not be in equilibrium. In the second system, the torque about the axis of rotation is balanced. However, these forces are pointing upwards, and so this system will move upwards and also not be in equilibrium. Finally, this third example shows that the net torques and the net forces are balanced, so this is an example of a system in equilibrium that will not move.
So for this lab, the equipment that you will be using is a force table, string, pulleys, masses with different weights, ruler, and you need a piece of paper. So for this lab's methods, we first made around an inch hole diameter on a white piece of paper. We then set 3 pulleys on the force table at 30 degrees, 180 degrees, and 330 degrees. We then passed string through this force table and through the pulleys, and we hung masses onto the string until it reached static equilibrium. To determine what masses to use, we first did 150 grams on the 330 degree angle and 150 grams on the 30 degree angle. And to find approximately how much mass we needed for the 180 degree angle, we calculated the y component of the force for the 30 and 330 degree angle, and that gave us around 260 grams. Once we found the static equilibrium, we drew the force lines of actions onto the piece of paper and chose a random rotational axis point to where we drew perpendicular lever arms to these lines of actions, and we found torque for each of these. Then we used each of these torques to find the net torque.
Okay, so the main equation that we use to find torque is torque equals force times the radius of the lever arm. So here we have a diagram of our paper. These black solid lines are our lines of action. So we put one at 30 degrees, 180 degrees, and 330 degrees. And then we put masses on each of these to set the system in equilibrium. So on the 30 and the 330 lines, we put a 150 gram mass weight. And then on this 181 to balance it out, we have a 260 gram weight. After that, we found the forces of each of them. So these two were 1.47 newtons, and this one was 2.548 newtons. After that, we drew the lever arms, which are perpendicular to these lines of actions, and then we measured the distance of these radiuses. So for the first one, we got 0.710 meters. Second one was 0.705 meters, and the third one was 0.516 meters. So once we have all this information, we can use the formula to find the torque on each of the strings. So the torque on the first string was 1.04 Newton meters. On the second string was 1.80 Newton meters, and the last one was 0.759 Newton meters. So once you find this, you have to find a direction. So to find the direction that it is turning, you take this axis of rotation and pretend that you're pulling it from your line of action. So as you can see, if you were to pull from this side, the whole system would be shifting counterclockwise. So this direction would be in the counterclockwise direction. And then for these two, if you were to pull them, you can see that they would both be turning in the clockwise direction. So here we put the clockwise. So to find the net torque, you just add up your torques. However, you have to keep in mind that some of them are going in a clockwise direction and some of them in the opposite direction. So I set my scale where the clockwise direction is positive and the counterclockwise is negative. So once I added them together and subtracted the counterclockwise one, we got a 0.00588 Newton meters in the clockwise direction. And our expected value should be 0 because if the system is in equilibrium, the net torque should equal 0. However, we're unable to find a percent error for this as our expected value is 0, but our absolute error is 0.00588 Newton meters. And this shows that our lab was pretty accurate and it was successful.
The principle that the net torque is 0 when an object is in static equilibrium applies across various fields, ranging from physics to engineering and even to biomechanics. In physics, this concept is fundamental in analyzing systems where forces and rotations must be balanced, such as a seesaw or a bridge. Engineers also apply this principle when designing stable structures like buildings or cranes, ensuring that the forces and torques are evenly distributed so that the structure remains in balance without tipping or just collapsing. Also in mechanical engineering, torque analysis is essential for understanding how machines and gears function smoothly without any unwanted rotation or strain. Even in biomechanics, our muscles and our joints rely on the balance of torques to maintain posture and control movement itself. Also in fields like architecture, understanding how the torque influences stability greatly helps in creating aesthetically pleasing and structurally sound designs. And after all that, the concept of zero net torque is a universal principle that plays a critical role in any situation involving balance, rotation, and equilibrium.